Alright, the objective today is to explain what the Intel manual says about the divide by zero and overflow exceptions. The processor reports a floating point divide by zero exception whenever an instruction attempts to divide a finite non-zero operand by zero. The masked response for the divide by zero exception is to set the ZE flag and return an infinity sign with the exclusive OR of the sign of the operands. So that last part is really cool because it explains the existence of the positive and negative infinities. And remember from our last video where the ZE flag is. There's two locations. You got that x87 FPU control and status word locations. So the ZE flag will be one of these bits 0 through 5, and or it'll be in the MX CSR register, probably same location. We got bits 0 through 5 right there. So the question's really short and simple. What happens if you try to divide by 0? Now the second one gets a little more complicated because I just really want you to soak in what's about to happen here. We've read 2 sentences so far, and there's a lot to unpack. So this says, what does an XOR operation accomplish? Like, what's the point of that? Let me help you out by giving you an example. You have the ZE flag now set, right? That's what it said in the manual. The masked response for the divide by zero exception is to set the ZE flag and return an infinity sign with the exclusive OR of the sign of the operands. So we have a 1, and infinity will be the result of trying to divide something by 0. Now, to determine whether it's a positive or negative infinity depends on what we were dividing in the first place. So I later say that you were attempting to divide -10 by 0. Okay, so that's the basis here. Now in binary, a 0 sign bit is for a positive number and a 1 is for negative. Simple, right? Not the case in 2's complement, but we're using floating point format, single precision, so not 2's complement. So if we have a negative number here, then we have a 1, so 1 XOR by 1 is 0. I can only get a 1 if this is 0 and 1, or this is 0 and 1. Not going to get it if they're both 1s or both 0s. So down here, we could see it flipped. If we had a positive 10 divided by 0, and we XOR the positive a 0 by 1, then we get a 1. But wait a minute, if we had a positive 10 and that leads to a 1 and a 1 is negative, you're saying that by XORing, I'm going to get a result, an infinity result of a positive number? So I'm making a bit of a leap here. I hope this is correct, but the part where it says the masked response. So a lot of times a mask will flip bits. Let's just try to read that in its entirety. The masked response for the divide by zero exception is to set the ZE flag and return an infinity sign with the exclusive OR of the sign of the operands. Whoa, then I wonder if it matters if the 0 is a positive or negative 0. So at this point, I think I have some really good questions to post on Stack Overflow, and I'll report back to you with the results. But if nothing else, we'll remember the day that I was doing part 38 of the Intel manual, and I was really confused, but made an inference, and now I just need to go test the hypothesis or ask somebody if that was a correct inference I made. Or maybe the manual will tell us or give us examples later. So let's continue. If the divide by zero exception is not masked, the ZE flag is set, and a software exception handler is invoked, in which case the operands will remain unaltered. So the next logical question is, can I finish reading this manual without going crazy? Just kidding, I should probably say something like, if the divide by zero exception is not masked, what will the exception handler do? And the answer is it will keep the operands unchanged. So in that sense, I guess we're just preserving the original equation. And then here's another question probably for Stack Overflow, because the sentence said, whenever an instruction attempts to divide a finite non-zero operand by 0. So I was wondering, what happens if you divide 0 by 0? Is that 1? So genuine question, what happens if we try that? The manual does give us some sections to refer to learn more about this divide by 0 exception, but they add this when detected while executing x87 FPU or streaming SIMD extension instructions. So I guess these are some special cases where divide by zero might act a little funky. Well, let's move to our numeric overflow exception. It says that the processor reports a floating point numeric overflow exception whenever the rounded result of an instruction exceeds the largest allowable finite value. That will fit into the destination operand. So if there's not enough bits and it won't fit, no surprise, we have ourselves an overflow condition. Table 4-9 will show us the threshold range for numeric overflow for each of the floating point formats. Overflow occurs when a rounded result falls at or outside of this threshold range. So keep in mind, if we're talking about single precision, we're talking about 32 bits. If we're trying to put a number that is larger than 32 bits into the destination operand, and that destination is only 32 bits, then yes, we'll have an overflow. We'll have a problem. So here's the table, not very insightful. Single precision can only go up to 2 to the 128. So that's interesting. We should remember our reading about this 754 standard, where basically this is the maximum exponent range we can get out of that. And then look at double extended precision. That is an enormous number. Well, I crossed off this paragraph. It's not particularly good, but for consistency's sake, let me go ahead and read it. When a numeric overflow exception occurs, and the exception is masked, the processor sets the OE flag, and returns one of the values shown in Table 410, and according to the current rounding mode. Maybe I wanted to skip this because actually, no matter whether it's masked or not masked right here, that OE flag will be set. A software exception handler is invoked, though, in this second case. In the first one, it's looking at the current rounding mode. But a software exception handler is invoked, and the source and destination operands either remain unchanged, or a biased result is stored in the destination operand. And I read that thinking, that's pretty genius. So I just ask, we can bias other things, like a destination operand? Not just an exponent? Now, depending whether the overflow exception was generated during a streaming SIMD extension floating point operation or a regular x87 FPU operation, that will determine if we're going to get an unchanged number or just a biased number. So that's a really good question. So what determines if the destination, this is the destination of the result of this overflow operation. So what determines whether that operand receives an unchanged result or a biased result? And so here's our table 410, masked responses to numeric overflow. I don't think it's particularly insightful, I guess. The rounding mode will determine what's going on. And as you can see, the sign will just be maintained throughout. They finish this section by saying, see the following sections for information regarding the numeric overflow exception when detected, while doing all those things we said before. So to finish off a particularly confusing section, let's just make sure you understand why the OE flag is called OE. What does it stand for? We're talking overflow exception. And so after you answer that, just look forward to the next video where I hopefully can clarify, number 2 right there.